Okay, so I just said I was going to make a little bit of a video about these couple of pages because this might help you with the physics that you need for your internal. So, looking at Hooke's law here, and this is what we mean when we're looking at Hooke's law. So, Robert Hooke was really looking at the fact that when you have got something elastic like a spring, the more you stretch something, the more force it will be able to produce. So in your internal, you're going to be thinking about a mass bouncing up and down on a spring. So the further you extend that spring, the more force it's going to produce. Now, also you will see that the force that the spring produces is going to be based on the extension. So here is x, and that's the extension of the spring, but also on K, which is the stiffness of the spring. Okay, so this force that the spring will produce is based on K and X. Okay, so here we've got two springs, okay, that we can extend here. So the larger the value of K, the harder it is to stretch. So the less stretchy your spring is, the higher value of K you will have. So it says here, why is there a negative sign? Well, if we think about what happens with the spring, so here's what we call equilibrium. Okay, and this, can't spell, equilibrium. And this is the point where your spring would naturally sit. Okay, so when you just leave your spring sitting still, that's where it would naturally sit. Then we extend it, so we pull the spring out by this amount, x. Now you guys know that when you pull that spring out, it will try and spring back in again. Okay, that's exactly what will happen. So there's a force trying to pull it back towards the equilibrium. So your extension will be in this direction, the force will be in the opposite direction. So that's why in this equation we have this negative sign here. It's just saying that the force is in the opposite direction to the extension that's producing the force. Okay. So when it says explain what Hooke's law means, we can just say that the force produced by the spring is proportional to the amount of stretch or the extension that we give it, or compression if we're squashing our spring in, and also the spring stiffness. And we can talk about the fact that the extension is in the opposite direction to the force that it produces. So if we look at these two springs, a thicker spring is going to be much harder to compress. This might be like something that you've got in the suspension of your car. This spring is going to be much stiffer, much harder to compress. So therefore, for the same extension, it would produce much more force than this spring here. Okay, so this one appears to be stiffer, and this one would be harder to stretch or compress. So we know then when we stretch a spring, we've got a force that it's going to exert, and the more we stretch it, the further we stretch it out, the bigger this force is going to be. So if we were going to draw a graph of force against extension, it would look like that. Okay. So when we stretch a spring, we've got to do work on it, and we know that that will cause it to store elastic potential energy. Okay, and we've looked at that in previous years. We've also just looked at the fact that work is force times distance, and that's going to be equal to our energy stored, because we said they were both. Okay, so what we've said then is that if we think about Hooke's law now, we've got F is equal to minus K times X. So if we rearrange that, we can see that K is equal to F over X. So as we increase the extension, we increase the force that our spring is producing, because we have to keep K, which is the spring stiffness, the spring constant, the same. Now, F is going to remain the same for any given extension. Okay. Now remember, be very clear about what you're talking about when you mean extension. So here's our spring just about sitting at its equilibrium position. Okay. So what you're measuring is the distance past that equilibrium position that you're going to pull your mass down by. Okay. So that's what you're measuring when you're measuring extension. Okay. So obviously this length is going to change depending on how much mass you've got on there, but the extension that you pull it through is obviously going to be the same, hopefully, each time. How big that extension is, you'll have to see whether that makes Okay, so once you've got your extension sorted out, then obviously if we've got the same extension each time, the force must remain the same. So the extension and the force are related. Force that you produce for the same extension must remain the same as long as your spring constant is the same. But what you will have to think about then is how that relates to Newton's law. So if you think about how that relates to F equals ma, that should help you then relate what's happening to what you're seeing with your time period. Okay. So as we've just said then, if we've got this relationship here, force spring produces is based on the extension. So as you increase x, you're increasing the force that you're producing. But if F remains the same for any given extension, as the mass increases, your inertia is increasing. And here's Newton's law that we talked about. Okay. So if inertia is increasing but the force for any given extension is remaining the same, acceleration must decrease. So if you've got a lower acceleration, you can think about how that's going to change your time period.